This is day 7 of Verilog Digital Design series. Today we are going to talk about multiplexers and demultiplexers. The multiplexer. It is basically known as many to one switch because it has multiple inputs and a single output. It is also called as a selector because when you have multiple inputs and you want to select any one of them, at that time we can use a MUX. See, it is written, the multiplexer selects one of the several input signals and forwards the selected input into a single line. Think of it as a rotary switch where the select lines determine which input reaches the output. Let us see how it works. For a MUX with two n inputs, you need n select lines. So if you have 2 is to 1 MUX, you will require one select line. If you have 4 is to 1 MUX, you will have two select lines. And if you have 8 is to 1 MUX, you will have three select lines. So we'll start with a basic example, 2 is to 1 multiplexer. We learned about this in the previous class when we talked about types of Verilog coding. I had mentioned the same slide there also. You can refer the previous video for that. Let's design a 2 is to 1 MUX. As you know, based on the select line, if the select line is 0, input 1 will be given as the output, and if it is 1, input 2 will be given as the output. This is the gate level diagram of the multiplexer, and this is the equation. See, here we have the logic circuit diagram of a 4 is to 1 multiplexer. So when compared to the 2 is to 1 MUX, what happens here is, since we have 4 inputs, we require 2 select lines. Based on this 2-bit data, we can classify what will be the output. If both your S0 and S1 are 0, you will get D0 as the output. Similarly, if you have 0, 1, you will get D1. If you have 1, 0, you will get D2. If you have 1, 1, you will get D3. Based on that, we'll write the Boolean expression for this. So what happens is, we write the output and the selected select lines. Here you have D0, S0 bar, S1 bar. D1, S0 bar, S1. For 1, you will not give the bar. D2, similarly, you have D2, S0, S1 bar plus D3, S0, S1. Since all of this is in OR gate, only one of the expression will have 1 and all the others will be a 0. And whichever one has the 1 will go out as an output. You have all the inputs and you have your two select lines. Both are given S0 and S0 bar because here you will require both of them, S0 sometimes and S0 bar sometimes. So you have the inverter to do that. And we write this Boolean expression. You can see D0, S0 bar, S1 bar. So we have taken D0, S0 bar, S1 bar, and this is an AND gate. Similarly, we'll do this for D1, D2 and D3, all the 4 AND gates. Now you can see that the expression is in the addition format. So we use the OR gate, 4 input OR gate, and this will give you the final output. See, now we'll see the Verilog code for the 4 is to 1 MUX. Module 4 is to 1 MUX. You know that you have 4 inputs. So you will write it in the form of a bit format, that is input 3 is to 0 input. And input, you need select line is also your input, right? So you have two select lines. So you will put a 2-bit select line. Then output reg out. So at all conditions, depending on the case, what is your code actually depending on? When you see the multiplexer, the output is completely dependent on the select line inputs. So I'll tell, based on my select line inputs, you give me the output. So if it is 2 dash, that means 2-bit 0 0, output will be input 0. That means if your select lines are 0 0, the first D0 will be your output. In a similar way, for 0 1 you will have input 1, 1 0 you will have input 2, and 1 1 you will have input 3. Also in the previous video we spoke about default conditions to provide to prevent latches. See, here I have used a default condition. What this does is, in case if there is any other input other than what we have mentioned here, default it will give a or if you haven't given any input, in case that time it will give a 0, 1 dash B naught, and this is the end module here. Now using that only 2:1 MUX, we are designing 4:1 MUX and a 8:1 MUX. Let us see how much. So to design a 2:1 MUX, what we'll do, we'll have one 2:1 MUX, two inputs and one select line. But for designing a 4:1 MUX, we require two select lines, right? So what we will do is we'll use another 2:1 MUX here and 2:1 MUX. So you have 1, 2, 3, 4 inputs. Based on these 4 inputs, we'll get one output here, one output here, and those two outputs will go to this as input, and you'll get the final output. In a similar way, for 8:1 MUX also it is same. You will have 8 inputs, and finally based for all those 8 inputs, you want to select any one of them. That will come as the final output. So in sometimes interview they might ask you how many 2:1 MUX are needed to create a 8:1 MUX. So you can see in the stages you require around 1, 2, 3, 4, 5, 6 and 7 to make a 8:1 MUX. In a similar way, for 4:1 MUX using 2:1 MUX, you require only 3. Now we'll read about demultiplexer. It is similar to multiplexer but opposite to it. There it was many to one switch, here it is one to many switch. A demultiplexer does the exact opposite. It takes the single input signal and routes it to one of many data outputs based on the select line. How it works? While a MUX is a data selector, a DMUX is a data distributor. This is a very important word to remember. Data selector. MUX is a data selector, DMUX is a data distributor. The non-selected outputs usually stays at logic 0. A 1:4 DMUX uses two select lines to decide which of the four outputs gets the input value. Let us see how it works. So you have a single input and you have multiple outputs. Module DMUX 1:4. Input is DN, and you have a 2-bit select line, so you will use S1 and S0 as select lines. Output, here your output is a 4-bit, or else we can tell 4 data outputs. I am registering it as 4 data outputs. Always at all conditions, that means star, I'll tell that my default value, if anything is not coming, y is 4 dash b naught. That means all the bits will have 0. I put case select. Based on the select lines, if the select line is 2 dash b00, y naught will get d in, and all the other outputs will be 0. B, C, D will be 0. 2 dash B naught 1. So A, C, D will be 0, whereas B will get this input as output. 1, 0, C will remain as the output and others will get 0. In 1, 1 condition, D will get the output and the other 3 will remain as 0. Let us see the key differences between a multiplexer and a demultiplexer. As I already told you, multiplexer is a data selector and this is a data distributor. Inputs. Here for a multiplexer you can have n number of inputs, but for a demultiplexer there is only one input. Here output will be single, but here output will be multiple. Here we are using parallel to serial conversion, and here you are using serial to parallel conversion. This will be very helpful in your data processing when you are using a MUX and DEMUX. We'll discuss about this in the next slide. Analogy. Several inputs leading to one door leading to several rooms. It is a simple way of understanding for you. See, real world example. In a simple communication system, a MUX and DEMUX works in pair. At the transmitter side, a MUX combines multiple low speed signals like voice or data into a single high speed transmission line. At the receiver, a DMUX takes a single line and splits it back into the original individual signals for the correct users. So this is the use case in real world application. If you have any doubts, feel free to put it down in the comment section. Thank you. Subscribe to EC TechNest.